representing constant acceleration. By the end of this lesson, we'll be a lot better, more proficient in graphing and dealing with position, velocity, and acceleration, all as functions of time, that can be used to find the relationship between those quantities. We'll be able to describe the position, velocity, and acceleration of an object using representations of that object's motion. To meet these objectives, we need to make sure we know that an object's instantaneous acceleration is the rate of change of the object's velocity, which is equal to the slope of a line tangent to a point on a graph of the object's velocity as a function of time. We should also know the displacement of an object during a time interval is equal to the area under the curve of a graph of the object's velocity as a function of time. The change in velocity of an object during a time interval is equal to the area under the curve of a graph of the acceleration of the object as a function of time. No vocabulary here because there's nothing new. So hopefully we can get through this nice and quick for you. When given position as a function of time, or position versus time graph, there are three ways we can pull information. First of all, we can pull data from the points. For example, this circled area, we can say at 3 seconds the position is 18 meters. Maybe we need that for problem solving. Next thing we can do is we can calculate the slope of a tangent line to get the average velocity for a time period. Remember, the slope of a position versus time graph will give you your velocity. Finally, we can plot the different velocities as a function of time. So we can take that slope and put it on its own graph. Perhaps the easiest way to do this is to fill in the blanks to these two sentences. Really, it's just one sentence just repeating itself to make sure you fully understand the relationship here. And our answer choices for the blanks will be either 0, positive, negative, constant positive, or constant negative. It'll make sense once we see it. All right, so the very first part of that slope, we would say it starts at or starts 0. Then the next part of this slope, we would say, then it goes positive. So we started at 0 because the very beginning parts were 0, which means our velocity started 0 and then it went positive. Next part, the slope starts positive and goes constant positive. I know that blue line is kind of squiggly. That's my own drawing skills lacking. But we're going to call it constant anyway. So because the slope starts positive and goes constant positive, that means the velocity starts positive and goes constant positive. Here we are on our velocity versus time graph on the right. We have our velocity starting at 0 and going positive, going towards a positive direction. And then it starts positive and it goes to a constant velocity, which is a flat line. Which brings us to velocity as a function of time. With velocity as a function of time, there's 4 ways we can pull information. We can pull data from the points. Again, at 3 seconds, the velocity is 18 meters per second. We can also calculate the slope of a tangent line to get the average acceleration for a time period. The slope of velocity versus time graph is acceleration. Memorize that. And we can plot the different accelerations as a function of time. And again, here's our starts blank and goes blank little game that we can play. So I'm going to make this a little bit difficult so that way it just doesn't feel the same, because for this, starts 0 and goes positive. We get it, but I want to let you see another example. All right, for this one, the slope starts positive and goes towards 0. Play that again. Look at the purple bar on the graph on the left. Starts positive and goes to 0. So our slope starts positive and goes to 0, which means our acceleration starts positive and goes to 0. That's why the graph on the right side, we're going down. Next piece, the slope starts at 0, because that's where we ended last time. Starts 0 and goes negative. So to show that on our acceleration versus time graph, we start 0 and go negative. This is a constant acceleration, constant decreasing acceleration on the right side. Our next part starts negative and then goes to 0. So each last little piece of the graph is now our starting point. Now the acceleration starts negative and goes to 0 as well. And then finally we're going to start 0 and go constant positive. Again, little squiggly line there, sorry. So the acceleration starts 0 and goes constant positive. Replay that a couple times until you really get the idea of what's happening here. This is about as tough of a graph as you're going to be dealing with in AP Physics 1. All right, then the fourth way we can pull information is we can calculate the area between the curve and the x-axis to find displacement. For instance, if we took the area of this first positive triangle, that would mean our displacement is 0.5. So because the velocity started positive and then it went towards 0, our position versus time graph needs to start positive and then go towards 0. Let me do one other little piece. The next little leg here starts 0 and goes negative. So we start at 0 and then we go to a negative slope. And it's a constant velocity, so we need to have a constant velocity. Then the next piece goes from constant velocity, constant negative, to 0, excuse me. So constant negative to a slope of 0. So we're changing, going in between this velocity versus time graph and the position versus time, and this is probably the most difficult piece here. So make sure you have those starts blank, goes blank down. All right, on to acceleration as a function of time. A whole bunch of information on this slide. I didn't go through and add animations just because you've already seen it. So here's all 4 different ways we can pull information from the acceleration as a function of time. We can pull data from the points, of course. We could say at 2 seconds our acceleration is 2 meters per second squared. We can calculate the slope of a tangent line to get the average jerk for a time period. Jerk is not covered in this course, but the derivative of acceleration as a function of time will give you jerk, which is your change in acceleration, or the rate that your acceleration changes. You'll see that in robotics and more complicated mathematics. Plot the different jerks as a function of time. We can do that. We're not going to, but we could. And then finally, we can calculate the area between the curve and the x-axis to find our velocities. We've done that several times. So here's our area at 1 second. We have this area which is constant and negative, so our velocity was also going to be constant. Or excuse me, increasing in the negative because we have a negative acceleration. I'm not going to do a worked example here because the examples that we went through, we're going to get practice in class. Next step is complete that practice. For more practice, use the AI prompt. Provide me with 3 practice problems for translating velocity. You can read. And then make sure you ask each other and then ask me and keep asking until you get it and keep practicing until it is really easy for you and you can't mess it up.